Going to go. I believe you're live. So, is the screen visible? Okay, great. Enable annotations for everyone. Excuse me. All right. So, yeah, continue to say you'll have to excuse my voice because it's still not apparently fully back to normal. But okay, so I think just to quickly recap where we were yesterday, we were trying to count the number of spanning trees in a graph. So we defined what a spanning tree is. We defined what the Laplacian of a matrix is. What's the Laplacian matrix associated with a graph is. And it looks a lot like the adjacency matrix, except the off-diagonal entries are minus ones instead of plus ones, and the diagonal entries are basically the degrees. So the ith entry is the degree of the ith vertex, and we are working with this sort of Laplacian, which is not the Laplacian of the whole graph. We knocked out the last row and column, where you can knock out any one that you like, and basically that's the object that we'll be working with. And we claimed that the number of spanning trees in our graph is the determinant of this smaller Laplacian, right? And we basically brought up the product form of the determinant and said we are going to stare hard at what we call the super expansion, which is write out the degree as 1 plus 1 plus 1 as many times as you need to, then write the determinant in product form, expand everything out till all your terms are basically products of plus ones and minus ones. And now you can think of every term in the determinant as basically saying that, okay, let me box a few entries in my matrix where the matrix is written out in this form. And as long as I've put one box per row and column, that's going to be a valid element in my super expansion. What's really key to remember is that these terms are weighted by a plus or minus one depending on the sign of the underlying permutation that brings this out, right? So that's those signs will actually ensure that we are actually performing our count correctly, because those signs will ensure that we have the cancellations that we need. But yesterday, for the most part, what we did was we focused on the terms in the super expansion that actually come from choosing plus one entries simply from the expanded sums in the diagonal. So we were essentially only focusing on the identity permutation. And we said, well, let's just collect plus ones from the diagonal terms. And we saw that the spanning trees show up when we do this. In particular, when we, and of course, I kind of vaguely said that we will be thinking of, I mean, I think it's natural that all of these plus one terms here correspond to edges, because there are only in the ith entry, the number of ones that you have is the degree of the ith vertex. So there's a natural 1-1 correspondence between the ones that you see and the edges incident on that vertex, right? So when you are picking out a set of plus ones like this, naturally corresponds to a subset of n minus 1 edges in the graph. And then I sort of fuzzily said that, okay, think of these edges as being oriented, and think of them as being oriented towards the missing vertex. But that was already a little bit vague, because, for example, you might have situations where this missing vertex is not even involved. So, for instance, what if you picked the green entry here, the purple entry here, and the blue entry here? There would be, these edges would not even involve this guy. So the orientation basically being towards the missing vertex is, I mean, I think that was just a visualization that I had that was convenient when we were actually working with spanning trees, but it's not a comprehensive notion of orientation. So let's fix that first, and I think let's just define these as oriented edges. So okay, now I think I'll just make this a little more precise by saying that every term in the super expansion can be associated with a directed graph on the full vertex set of the original graph. So we're looking at all the vertices from 1 to n, Okay, but we're looking at terms in the super expansion of this L minus, so this Laplacian with one column and row missing, right? So every term in this super expansion can be viewed as a directed graph on the vertex set 1 to n in the following fashion. Okay, so if you have a -1 that is being circled, which is one of the off diagonal entries, then you introduce an edge from I to j if that -1 entry is in the ith row and the jth column. So you introduce an edge that goes from I to j, but this edge we will call a negative edge. So most of the edges that we've seen so far are actually not negative edges because they've been coming from the diagonal entries. But from the off diagonals, the edges that we will add, we will call them negative edges. And now from the diagonal entries, so if we have picked up something, we have pulled out one of the plus ones sitting in a diagonal entry sum, then basically what we are looking at is a positive edge. And again, it's oriented from, so it's the ith diagonal entry. So the edge starts from the ith vertex. But where does it go? Well, if the kth one is circled, then it goes to the kth smallest neighbor of I. This is a way of making precise what I was just doing with colors yesterday. So yesterday I was saying that, well, if you look at these, 1 plus 1 plus blah, 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 ones, you look at degree many ones sitting in the ith entry, I was mentally associating each of those ones with an edge. So there was a one-to-one correspondence between the ones in the expanded form of the ith diagonal entry and all the edges incident on the ith vertex. I did not make that correspondence explicit, but you could do it by saying that, well, look, all these vertices have labels, right? The label from 1 to n. So you basically, when you're looking at any of these diagonal entries, it's basically, I mean, you're looking at all the edges going out of the ith vertex, and they're going out to all of these neighbors. You can order the neighbors by their labels. And so if you have boxed the kth entry, in the ith row, ith column, you box the kth entry, then you add an edge from the vertex I to the kth smallest neighbor of the ith vertex. So the coloring here is consistent with this definition, I should hope. So for instance, here, if you look at the third vertex, so 3 has neighbors 1, 2, and 4. So 1 is the first one here, and the blue neighbor 2 is the second one, and the highest labeled neighbor is the third one. That's the orange one or the golden one or whatever. So when you box the last entry here, I'm going to pull out, or I'm going to draw the edge from 3 to basically, if you didn't have this notion of an ordering on the neighborhood, or if you didn't make explicit a mapping between the ones sitting in the sum and the edges incident on the vertex, then you would just run into a little bit of ambiguity saying, well, I've picked this one in my super expansion, which edge does it correspond to? But now I know, because the ones in the sum are ordered, and I've mentally associated an edge with each of those ones. So I know which one I'm picking out. So if this one is boxed, it's going to be this edge. If this one would have been boxed, then it would have been the edge from 3 to 2. And if the first one here would have been boxed, then it would have been the edge from 3 to 1. So are the directed edges associated with any entry in the matrix, and therefore the collection of directed edges associated with a term in the super expansion? Are these two concepts kind of clear now? Give me a +1 if this directed subgraph associated with a term in the super expansion makes sense. Okay, fantastic. So we have these terms, and we have the directed graphs associated with them. And here's an example, for instance. So here's the anti-diagonal. I think I didn't quite say this right when I wanted to do this example yesterday. Now, hopefully it's fixed. So you see that the first row, the third -1 is highlighted. The third column is highlighted, and that's a -1 entry. So we're going to have a negative edge from 1 to 3. So that's one of the negative edges from 1 to 3. Now we have a diagonal entry highlighted in the second row. So second row, second column. So 2 has a positive edge going towards its least labeled neighbor. So that's an edge from 2 to 1. And in the third row, what's going on is that there is an edge to the first column, or we've pulled out the entry in the first column. So we have the edge from 3 to 1, and this time it's a negative edge. So that's the situation. This is what a typical directed graph associated with a term in the super expansion looks like. You could have an example where you have no positive edges at all, and this would be one such example. You can verify that the orientations hopefully make sense. Now, I think, let me see if I can at least at an intuitive or partial level address the question that I think Vinay brought up yesterday, which was that if you look at, I think I started by looking at spanning trees and saying that if you look at the edges of a spanning tree, I can map them to terms in the super expansion that come from the identity permutation, right? And we looked at all the 8 spanning trees yesterday. We conveniently oriented them towards the missing vertex and, picked out this collection of edges. And I think, trying to convince you that all the spanning trees actually manifest in the super expansion as +1 terms. So at least we know that to some extent they get counted. Now, that count may be perturbed by what's going on with all the other terms, but then the hope is that we show that all the other terms neatly cancel. But I think there was a question of, how do we know that the spanning trees don't manifest elsewhere? We know that. Okay, I think what we do know is that if we pick out, okay, so maybe let me just walk through this and we'll see if this makes sense. Okay, so suppose you give me a spanning tree, and right now notice that I have no orientations and I have no commitment to black or red right now. I have no commitment to whether these edges are positive or negative. But I'm going to try and think about which term in the super expansion most naturally captures the spanning tree or is associated with spanning tree, and is there more than one? Yeah, could there be to some extent an ambiguity? Could there be multiple terms in the super expansion that correspond to the spanning tree? Let's just think about that for a minute. So let me start with this edge, the edge between 4 and 3. Can this edge correspond to a -1 entry? Is there any -1 entry that captures an edge between 4 and 3? Remember that 4 is the missing vertex. And remember that we have knocked out the 4th row and the 4th column, right? Okay, so the answer is no. And so, yeah, thanks, Janki. Hopefully that's clear. A -1 entry that captures an edge between 4 and anything else would have to be either on the 4th row or the 4th column, both of which are not available to us. Is that clear to everyone? Give me a +1 if that makes sense. Yeah, okay, excellent. So this edge has to be a positive edge. And because we know the other endpoint, we know that this is an edge connecting 3 and 4, we know that this must in fact be this entry out here, right? So the super expansion definitely has the last one in the from the 3-3 entry, basically, right? So this I think we can deduce and be sure about. Now, what about this edge, the one between 3 and 2? What can we say about that edge? Can that correspond to a -1 entry? In a priori, it can, in the sense that there are 2 -1 entries that actually correspond to this edge. So there is the -1 entry in the second row, third column would be this edge, because that's the edge between 2 and 3. And there's also the entry in the third column, third row, second column. So these two -1s actually naturally correspond to this edge here. But could we have picked them in the super expansion term that already has this? Exactly. It won't be picked by a permutation, right? So I think this is something that I had as a typo yesterday, but we know that, well, it's not going to happen. So these entries are not compatible with our current choice of this fellow here, right? So in principle, this edge could have been a negative edge, but given that we have already picked out the edge 3, 4 as a positive edge, the edge between 2 and 3 cannot be a negative edge because that would basically conflict with the existing choice. Yeah. So this has to be a positive edge. And there's only one way that that positive edge can go. So I think on the next slides, I have these. Yeah, so if it was the negative edge from 3 to 2 or from 2 to 3, those would end up contradicting our current choices. So we wouldn't have that. And the positive edge, notice that that also has to go like this. It can't be the positive edge oriented away from 3 because then that would mean picking another +1 from the same term, and that would be too greedy of us. We cannot get 2 +1s from the same diagonal term in a permutation, right? So this is also forced to be a positive edge, a positive edge whose orientation is also forced, okay? And any guesses on what can we say about the last edge? Can the last edge be a negative edge? No, and again, I think it's for similar reasons, right? So 1, 2, that edge between 1 and 2 is witnessed by 2 minus 1s in the Laplacian. So you go from either the first row, second column, or second row, first column, but both of them are blocked out by our most recent acquisition. So we cannot really have either of those show up. So this last edge also is forced to be a positive edge. And once again, the orientation is also forced. You cannot have it pointing away from 2 because that would mean that you have picked 2 things from the 2, 2 diagonal entry, which is not done. So it would have to be this way.
So why they are blocked out may not be clear to some.
Right. Yeah, so this is, I realize that this is proof by example at the moment. Okay.
No, I think just to say that, the moment I pick one element, right?
Right.
I think just to remind people that you can't pick any other element in that particular row or column.
Oh, right.
I
Okay.
think,
Sure.
So
Yeah,
if I've
sense.
picked up this element, then I can't pick up anybody in this row, this column. Similarly, because I picked an element here, I can't pick anything else in this row and this column because I'm allowed only one element in any row or column. Okay. So therefore, I'm forced to choose the final entry from here. Okay, I think this.
Right, exactly. Yeah, thanks. Thanks very much. So yeah, indeed, that's the idea of these super expansion terms corresponding to somehow an underlying permutation enforces this blocking idea that you can't, because you're working with a permutation, you can't afford to have repeats on rows or columns because then you're not a permutation anymore. And that's exactly what Vinay made explicit. And Jayati also has a nice analogy. I think it's a little bit like Sudoku. Yeah, you can't repeat a number on a row or column. So Sudoku definitely has a strong permutation vibe in each of the small boxes as well as when you go across rows and columns. So that's exactly the spirit of the constraint in some sense. So yeah, hopefully we can see that working our way backwards. So first of all, any spanning tree or any subset of edges that makes this big claim about being a spanning tree has to be inclusive of the missing vertex because a spanning tree connects everybody, leaves nobody out. So there's at least one edge of the spanning tree that's incident on the missing guy. And notice that the missing guy is never involved in a negative entry because that poor thing, its row and column have been knocked out. So the only way that you can basically be manifesting edges on the missing guy would be through these, positive ghosts that are sitting in the diagonal entries. So you'd start from there, but as you work your way backwards, you realize that it's becoming impossible to manifest the negative edges anymore because you seem to be stuck in a positive loop. That seems to be happening in this example, but it turns out that that's actually a property of how things are at the moment. And let's just try to argue that by making it explicit. So in fact, let me just summarize with a few properties of what's going on with these directed graphs. And hopefully most of this will feel natural, and we'll end with the thing that we just said, more or less, maybe a contrapositive of it. But okay, so again, keep in mind that what we said was that if you give me a term in the super expansion, I'm going to take the elements of that term and map them out to edges. So if I have a -1, it's going to be, so basically, okay, if you give me a super expansion term, because it's coming from a permutation, think of it as for every row, you tell me from which column do I pick my entry in the super expansion. And if it happens to be that the column index matches the row index, I have a diagonal entry, then you also have to tell me which +1 am I picking. That's what a typical term in a super expansion looks like. And if I picked a -1 term, that's a negative edge from I to j. And if it's a +1 term, then that's going to be a positive edge from I, the row index, to the kth smallest neighbor if you're picking the kth one from the diagonal sum. So that's a recap of what the graph construction was like. I should have actually gone back here where it's written out, but yeah, hopefully we can keep this at the back of our minds. And let's go back to these properties. So we do know that every time we put in a directed edge from I to j, then that pair ij was an undirected edge back in the graph G. Hopefully this is clear, because the directed edges are only either coming from -1 entries, which literally represented edges by definition, or it's coming from the +1 entries on the diagonals, which also we have implicit, we kind of made actually explicit an association of how the +1s correspond to edges. So every time you're adding, so you're never adding a directed edge between two non-adjacent vertices in G, right? So hopefully that's quite clear. Now, let's see, every vertex is exactly one outgoing edge, and n has no outgoing edge. So by an outgoing edge, I mean, so if I have a vertex, an edge like that would be an outgoing edge. And again, keeping in mind that we are working with permutations, is it possible that we added two edges like this? So this is, let's say this is some vertex I. And is it possible that we added edges to vertex j and some other vertex j prime? Can this happen? Let's just think about when would we add these edges. And we don't have to worry about the sign at the moment, but just positive or negative. Yeah, this is not possible. And just try to reason this out. Well, I mean, if you added an edge from I to j, that means that your permutation set picks the jth column entry from row I, right? But you've also added the edge from I to j prime. So seemingly your permutation also said pick the j primeth column entry from row I, but if it's a permutation, it's not going to give you those conflicting instructions, right? So some things, yeah. So they would be exactly, so j and j prime would be two circled entries in the same row. And in particular, that would be row I, and that would not be consistent with the idea that the super expansion term is coming from a permutation. So indeed, we will only see one outgoing edge per vertex, with the exception of the last vertex n, because the permutation only lasts for the first n -1 rows. The last row is simply not there. So we don't create any outgoing edge on n because we have no instructions to do so. Okay. Every edge that comes onto n is positive. So okay, let's see. So Janki has a question. What if there is an edge from 3 to a new vertex 5? Okay. Well, okay, the graph that we are considering, we have 4 vertices and we knocked out the 4th row and 4th column. If you have 5 vertices, then presumably you would have L minus would have 4 rows and 4 columns, right? And if there is an edge from 3 to 5, I'm not sure if you're asking what happens in terms of, if this edge belongs to a spanning tree, then when does this edge materialize in the super expansion? That would happen from the 3-3 entry, which would have 1 plus 1 plus as many times as 3 has neighbors, and 5 would be one of those neighbors. So that's the same role that these orange plus ones are playing here. So if you have a new vertex 5, if you have a fifth vertex, then L minus would have 4 rows and 4 columns. So I don't know if that helps with addressing whatever question you have in mind. Yeah, okay, all right. So yeah, I mean, the edge from 3 to 5 will not explicitly manifest as a -1 ever, but it will show up as a +1. So yeah, so which is exactly the point that we were making, that all edges that come on to N are positive. So first of all, the vertex N, the missing vertex, does not have anything going out of it, but everything that lands on it coming from other vertices, that those must all be positive, simply because, well, if it was a -1, well, how could it be a -1? Because suppose you have an edge from I to N and it's -1, that means you were picking up the -1 entry from the ith row and the nth column, which doesn't exist, right? So the only way that you did the I to N edge was because you went to the ith entry, which was the ith diagonal entry, and from there you picked out the +1 edge. So that's why that's going to be a positive edge, right? So right, so all edges coming onto N are positive. And okay, this is kind of key to our understanding of these diagrams. So no vertex is more than one negative incoming edge. Well, this and the next point combined will, I think, clarify or hopefully help us understand these directed graphs better. So no vertex is more than one negative incoming edge is kind of similar to when we said you cannot have more than one outgoing edge. So let's think about this. So if you have a vertex and you have two negative incoming edges, what does that mean? So let's say this vertex is I, and you have a negative incoming edge from J, and you have a negative incoming edge from K. What does that mean? So then can you again contradict the permutation vibes that we have here? So we have to think about, yeah, we end up at the same column, exactly. So we have to think about, when did we add the edge from J to I? We added it because we wanted to pick out the entry in the ith column from the jth row. But then if we added the edge from K to I, we again picked the entry in the ith column from the kth row, which means that the ith column is contributing two entries, which is not possible, right? So those were exactly the blockages that we were talking about earlier. So we don't have this situation. So every vertex has at most one negative incoming edges, one negative incoming edge. Yeah, exactly. So that's the sentiment also in the chat. Okay, so the next, and I think for now the final claim is that if you have a negative incoming edge, then your outgoing edge, so remember that other than N, everybody has exactly one outgoing edge. But if you have a negative incoming edge, then the outgoing edge is also negative. Does that make sense? Because again, suppose not. So suppose you have this edge incoming, which is negative, and you have an outgoing edge, which is positive, right? So let's say you have an edge from J to I, which is negative, and from I to K, which is positive. What does that mean?
You can
Right.
just annotate that. I think you're saying this is positive, right?
Yeah. So right, I'm saying, what if
This is positive and this is negative.
correct. Thank you. Yes. I want to say that if we had a negative incoming edge, then the outgoing edge cannot be positive. there is only one outgoing edge. So if it's negative, it can't be positive. So yeah, that's the claim. I think Janki is saying the ith row and the ith column is selected. That would be true in the sense that if the ik, the edge from I to k is positive, that means we must have picked out a +1. In fact, yeah, there must be a +1 that was picked out from the ith entry. But then there is a negative edge from j to I, right? So what does that mean? That means that, yeah, so we have also picked from when we went to row J, we've also picked the entry in the ith column. That's this negative edge here, right? So the ith column is again contributing from the diagonal entry as well as the off-diagonal entry from the jth row, right? I think that's exactly what Janki has in the chat. So hopefully it's clear that this is...
I think it's a bit easier with the picture. I'll just draw.
Yes, please. Thank you.
So if I have the jth row here, and I go to the ith column here, then I'm picking up this element. That's the negative thing. But then if I look at the ith, if I had to pick a positive edge from I to k, I can only pick it up from the diagonal entry between I and I, because it's a positive entry. But then you would have picked up two entries from the same column, and that's not possible. Right?
Yes.
Yeah, is that accurate?
Indeed.
Yeah.
Indeed, that's exactly what I wanted to say. So yeah, that's perfect. Thanks. So that picture is a much nicer version of what's it's the same thing here in text. So you've picked two things from the ith column. That's not feasible. So if you have a negative incoming edge, then you must get out on a negative outgoing edge. And hopefully all this is building some intuition for what things that are not spanning trees look like, and why, when we did have a spanning tree, we basically did not run into any of the negative edges, because in some sense, once you have negative edges, you kind of are literally going to be stuck on sort of some sort of a negative loop. But we know that we can't afford to have loops when we have spanning trees. So all of these are kind of general ideas that I'm kind of throwing out here. But maybe let's just go and okay, I think I will. Okay, thanks. I've just clear the annotations for a bit. So here, for instance, so I guess, yeah, I think we do agree that when we have these things that are spanning trees, what we can do is come up with an orientation of the spanning trees so that we get terms in the super expansion that correspond to +1, where the underlying permutation is the identity permutation. So that's all that we were doing yesterday. And if you go back and look at some of these examples, essentially what's happening is we're saying, well, just orient, you can do this recursively if you like, just orient the edges towards the missing vertex. You know that the missing vertex is involved, so it has a bunch of edges coming on it, at least one. So all of those edges are oriented towards it. And that's how it must be. These are positive edges. And then you work your way backwards to recover a full orientation of all of the edges that are there. And this will correspond to a term in the super expansion, which, because these terms are all positive, they all correspond to the identity permutation, which turns out it has positive sign. So it's a product of +1 entries. The permutation also has a +1 sign. So we are happy all of these spanning trees contribute a +1 to the sum. Now we want to argue that anything else, any other entry in the super expansion, basically must, so yeah, so we want to say that all the other entries, all the other elements of the super expansion actually correspond to things that have cycles. And in fact, they're such that they can be paired off so that they cancel. So the terms that we saw this way, by starting from the spanning trees and saying, hey, look at these terms, those terms are actually in 1-1 correspondence to the trees, because we're not going to see any other terms that either overcount the trees. All the other ones are going to end up having cycles, basically. So, and that's something that, well, I think it's just a realization that I've convinced myself of by just looking at these properties and staring at them hard enough. I don't know if I don't know if you're making a convincing argument about that right now, but anyway, let's just go ahead and look at an example of a cancellation just to get some intuition. So what I want to say is look at something that's potentially not a spanning tree, or look at some other, so look at any other term in the super expansion. So I think, just to be fair, the way this is presented in the miniature is, well, don't look at the terms in the super expansion, but look at the graphs that you get. So you have this whole list of terms in the super expansion, and each of them correspond to they correspond to these diagrams, right? So from the terms in the super expansion, you're going to get some edges in the graph, right? And I think the way they like to classify it is to say that, okay, you have some of these graphs that correspond to spanning trees. These are the nice objects that you want. And then you're going to have things that are not spanning trees. And some of them have a positive sign and some of them have a negative sign. And the sign of a digraph or a directed graph is simply the sign of the term of the super expansion. So that is all the plus and minus ones combined in that term multiplied by the minus one raised to the sign of the permutation. So it's basically the sign of the term in the super expansion, the overall sign, however it comes about. So we want to say that all the things, so you have basically all of these nice things, which are the things that you want to count. These are the spanning trees. So basically, look at the super expansion terms and in your mind replace all of them with these directed graphs. And now we have that, well, some of these directed graphs are basically orientations of spanning trees. So you get those fellows and you get them, you basically get them without repeats. And then you get a bunch of other terms whose sign in the super expansion is a -1, and a bunch of other terms whose sign is a +1. And all of these fellows are not trees, they have cycles, and they're all going to cancel out. And what I will try and do is show you an example of how we expect the cancellation to work. And I'll only do this somewhat by example and hope that the general idea carries through. But let's look at a typical object with a cycle. So here is, for example, a thing which has, so we're going to look at a canonical cycle. So if I give you a subset of edges, so we start with a super expansion term. It corresponds to a set of edges back in the graph. And those edges, let's say it's not a spanning tree. So there is a cycle somewhere. There might be multiple cycles. So let's just look at that cycle, so for every cycle, look at the smallest labeled vertex in it. And among all cycles, just pick the one that can claim to own the smallest indexed vertex globally. So we basically pick, in some sense, that cycle to be sort of the representative object. And so I look at, so here, for instance, here, there's only one cycle, so I don't have to choose anything. But that cycle already has the vertex that's labeled 1, as coincidentally the globally lowest indexed vertex. So yeah, we have this cycle here. And what I want to do is, okay, so notice that in a cycle, you cannot have mixed signs, right? So a cycle will either only have negative edges or only have positive edges. And if a cycle has at least one negative edge, then you know that that edge is incoming for somebody, and then the outgoing edge must also be negative. So you complete, and you only have negative edges. And this also proves, I think, that you cannot have mixed edges. So either if you have at least one negative edge, all of them are negative. Otherwise, you have 0 negative edges, which means all the edges must be positive. So you start out with this cycle without loss of generality. Let me say that the representative cycle has only positive edges. But then there must be a term where I can just say that, okay, let everything else be the same, but let me color these positive edges, let me color them negative. And that just takes me to a different term of the super expansion. Okay, so notice that here the positive edges correspond to these two entries in the diagonals, But if I flip it, then I go to these two off-diagonal entries, right? And hopefully it's clear that you don't disturb the permute, that this is a valid recoloring to do, right? So if I start with a cycle which has only positive edges, that's basically like saying that in the permutation, all of these, in the permutation, what was happening was that this was the permutation where 2 was going to 2 and 1 was going to 1, right? Because, yeah, let's see, that's, in this case, the permutation is only picking, it's the identity permutation. So these are all basically fixed points. And when I switch these out, right, what am I saying? So in fact, I have a longer example of an abstract cycle later. So maybe let's just go there. So if I start out with this cycle, let's say these were the labels, right? 1, 2, 4, 7, 5, 6, some random labels. And I suddenly say that, okay, let's take all of these positive edges and make them negative, right? So let's take all of these positive edges and make them negative. What happened to the underlying permutation? Which super expansion term have I moved to? Well, to begin with, I had, because these guys were all positive edges, I'm looking at these edges were basically being picked out from the diagonal entries, right? So when I say that, 1 to 2 is a positive edge, that means that look at the 1, 1 diagonal entry and pull out something. When I say 2 to 4 is a positive edge, that means look at the 2, 2 diagonal entry. 4 to 7 is a positive edge, look at the 4, 4 diagonal entry, and so on, right? So all of these red edges, these positive edges, were plucked out of the corresponding diagonal entries, right? So as far as my permutation was concerned, which was dictating how do I pick entries, on 1, 2, 4, 7, 5, and 6, this permutation was basically identity, right? On the rest of the graph may have another 100 vertices. I don't care about what the permutation is doing there. But on these select 6 entries, the permutation is fixed. Is that fair? Does that make sense? So when I look at this cycle, when I say that this cycle is present in some graph corresponding to, you've given me a graph or you've given me a collection of directed edges corresponding to some super expansion term, I go and look for a cycle. I look for the cycle that contains the smallest indexed vertex. I find one, let's say it looks like this. And I'm wondering, well, what can I say about the super expansion term that this structure came from? And that super expansion term, I don't know what else it's doing. I can find out by looking at the rest of the edges. But at least just by looking at this cycle, I know that the super expansion term must have hit the 1, 1 entry, 2, 2 entry, 4, 4, 7, 7, 5, 5, and 6, 6. Is that okay? Because I know that these are all positive edges, right? I know that. Okay. So now, okay, great. Thanks. Now, if I just change these positive, if I just recolor these edges and I say, okay, let me just think of these as negative edges instead. Do I just go to another valid super expansion? Well, now, instead of 1, 1, I know that this 1, 2 edge is now a negative edge. So I have to go from, I have to look at the second column in the first row, the fourth column in the second row, the seventh column in the fourth row, the fifth column in the seventh row, the sixth column in the fifth row, and the first column in the sixth row. Okay. But my point is that the only things that get affected is basically local to these guys. So maybe if we just do a smaller example, just with I don't know why I picked such a random set of indices, but let's just say you're doing a small triangle and you have 1, 2, 3, right? So originally you have 1, 1, 2, 2, 3, 3. But now somebody comes and says, well, no, instead it's 1, 2, 2, 3, and 3, 1, right? So you've just, thrown away the diagonal entries and moved to the off-diagonal ones. So that's exactly what Jayati is saying. And the point is that the rest of the permutation is undisturbed, right? So yeah, the arrows is basically the permutation that you want. So 1 is mapping to 2, 2 is mapping to 4. It's kind of like that. Yeah, exactly. So I don't know if it's worth 1, 2, 4. So this is 1, 2. I'm leaving out the 3, 4, 5. It's horrendous, sorry. So with the original permutation, we were just picking fixed points on these diagonal entries. But now I'm saying instead that from 1 I want to move to 2. From 2, I want to move to 4. From 4, I want to move to 7, which I think should be the last thing. And from 7, I want to move to 5. From 5, I want to move to 6. From 6, I want to move to 1. So something like that. The point is that previously we had, like on this region, we just picked out all the diagonal entries. Now all that we have done is basically done a reshuffle, which is very local to this. And the reason I'm pointing this out is to say that we won't end up contradicting the behavior of the rest of the permutation. We won't have any row or column complaining that, oh, you came on and, created a blockage, so this is no longer a valid permutation. You won't have that issue because you basically cleared out the diagonal entries and created all this room for yourself. And now all the stuff that you're picking is within the safe zone. So you're not going to say the 9th row and picking something from there where something else was already being picked and so on. So this is a very local reshuffling. Are we on board with that? Give me a +1 if you think you can go from, like, you can recolor all the positive edges to negative and go to a different super expansion term. Okay, good. So basically this is supposedly the bijection, right? Between the positive and the so if you give me a super expansion term which has a cycle, right, then I can give you a different super expansion term, and that creates a bijection between you can argue, I think that also requires a bit of an argument, but this is, I think, a reasonably clearly invertible mapping. So it's a mapping between super expansion terms that have cycles. All we are saying is pick a representative cycle and recolor the edges. That's go from positive to negative or negative to positive. So that makes it a bijection. But it still remains to be argued that this is a useful bijection in the sense that if two terms are paired up, one of them is a +1 and the other one is a -1. You still have to argue that. And okay, so that requires understanding what the sign of a permutation means, because the sign of a permutation contributes to the overall sign of the term. And I'll only say this like at a very, very high level. So the sign of, if you think about the sign of the term, the super expansion term that corresponds to a set of edges, well, that's going to be the sign of the permutation that gives you that term, whatever that means. If you already know it, that's great, but otherwise, that's some black boxy thing. And it's -1 raised to m, where -1 raised to m, where m is basically all the negative edges that you have, right? All the negative edges that you have will essentially end up corresponding, contributing -1 entries, right? So yeah, basically look at any directed graphs that you have. If you simply look at all the negative edges that are sitting there, in my convention, these are all the black edges. All the negative edges correspond to -1 terms. So m is basically the number of negative edges. So -1 raised to m times the sign of the permutation. This is the overall sign of the super expansion term. And I want to say that, well, if you started out with this term being a -1, then when you recolor these edges, it's going to flip to +1 and the other way around, right? So the point is that not much has changed between these two. Like, what's the difference between these two graphs, right? Or what's the difference between these two permutations? So I've knocked out, so assuming we started with this cycle which had all positive edges, and now I recolor them to negative, then of course I've introduced, how many -1 terms have I introduced? In the other super expansion term, I'm now seeing -1s which were not there in the original super expansion term, right? So how many in this example, how many -1 terms have I introduced? So remember that in the super expansion term that this graph is coming from, all of these edges were positive, right? So they all contributed +1 to that super expansion term. And there are 1, 2, 3, 4, 5, 6, 6 of them. Yeah. Now, when I go here, I've just said that, well, flip all of these guys to negative. So I'm going to the super expansion term where this cycle is a negative cycle and all of these edges are -1. So how many in that super expansion term? So let's say I start out with a super expansion term P and I map it to another term Q. So compared to P, notice that all the other edges are exactly the same. We'll come back to worrying about the sign of the permutation. But other than the cycle, everything else is the same. In this cycle, each of the 6 edges in this cycle contributed +1 to the super expansion product. When I wipe it out and I say change everything to -1, how many -1 terms am I getting extra relative to the original super expansion term? Number of edges, exactly. So I'm going to get -1 raised to 6. Yeah, exactly. So all of these edges contribute -1. So the number of extra -1 terms that I have in the product is going to be basically -1 raised to the number of edges. So if this is an odd cycle, I've already flipped the parity. If it's an even cycle, I've maintained the parity or the polarity, whatever is the right thing to say. Okay, so the sign is preserved if this is an even cycle. If it's an odd cycle, the sign is flipped, which might make us a bit nervous because we basically want the sign to always flip, right? So there is another thing that affects the overall sign, and that's the sign of the permutation, right? And the sign of the permutation is basically the number of transpositions in a cycle decomposition of the permutation. And if you already know what that means, that's great. I always struggle with the concept of seeing a permutation as a composition of transpositions. It doesn't help that this breakup is not necessarily unique, but the parity is always preserved. But anyway, the high level idea is that basically in this base permutation that we started out with, all of these were fixed points, right? So we said that these are all, the 1, 1, 2, 2, 4, 4, 7, 7, 5, 5, 6, 6 diagonal entries. So these are all 6 fixed points. So if I want to morph this permutation into this one, I can do it using 5 extra transpositions. Okay, so basically the sign is going to, the sign of the permutation is going to flip. So if this is an even cycle, what will happen is what you add in terms of -1 raised to 6, that preserves the polarity. But the sign, because you have meshed 6 fixed points into one cycle of length 6, in some sense, what you have done is you've taken your original permutation and you have added 5 transpositions. Essentially, you can think of it as how many more pairwise swaps do you need to do to get to the, to get to the long cycle. So, you can imagine small loops sitting at each of these vertices, and then one transposition will say, okay, exchange 1 and 2. But then that gives you a 2-length cycle. Now you want to bring 4 into the loop. So you say, okay, 1 goes to 2, but now 2 goes to 4 and 4 goes to 1. So you do another transposition. So by repeatedly doing this, you need, in general, to create a cycle of length x out of x fixed points, you would need x -1 transpositions. So if you had an even cycle, the -1 raised to the length of the cycle would not change the polarity, but you would have an odd number of transpositions being applied to the base permutation, so that will flip the polarity. On the other hand, if you had an odd length cycle, then the number of transpositions you need will be even. So the sign of the permutation stays the same, but now you're hitting it with a -1 raised to the length of the cycle, which is now odd. So that will flip the polarity. Okay. So something happens. So you have to basically just think through the cases a little bit.
Can I just add something?
Yes, please do. I think I'm sounding like a confused mess. So please go ahead.
Yeah, no. So all that she's saying is that you're looking at some cycle. Let's say the cycle has some length k. Okay. And if all these things become -1, remember that initially they were all +1, now they become -1. So they become -1 to the power k. But the number of transpositions in a k cycle is k minus 1. So you get a k minus 1. So this becomes -1 to the 2k minus 1. And this is always odd, and therefore you will always get a -1, which means that your overall sign has flipped. Is that
Yes, thank you. Yeah, that's
okay?
quite clear.
Yeah,
Yes,
yeah,
thanks.
that's about all is happening. Okay. So you're getting a k, and then you're getting a k minus 1. It doesn't matter the original k was even or odd and so on. The number of transpositions that you get is k minus 1. Initially, they were all, self loops in some sense because you picked them all from diagonal elements. So they were not doing anything. Now you're taking these and you're making them into a cycle. Okay. So the number of transpositions that are required to go from here, from the cycle back to this state, is k minus 1. Okay. And so that's roughly the idea.
Yeah, no, that's exactly right. I think the odd even bifurcation in my mind was just superfluous case analysis clearly. But yeah, I think this is exactly right. The number of edges in the cycle contribute k minus ones. The sign change of the permutation contributes another k minus one minus ones. So overall, at least 1 minus 1 will come out and survive. So yeah, so 2k minus 1 always being odd is exactly the key to this argument. And so you do have a sign change when you go across this bijection. All these other terms collapse. And I hope it was reasonably clear that there are only these three kinds of terms that are nice, that correspond to the spanning trees, and everything else which is guaranteed to have a cycle. I think I have a sense that maybe there were things that I think I should have certainly said more precisely, but I will say that everything can eventually be pieced together from all the fragments of information
No,
that
I think no, I think mostly there. So if somebody, I mean, we have spent enough time that it'll be a shame if somebody goes back with with some doubts in mind. So is there anyone who doesn't understand or who's
yeah, I think do let
any
us
questions
know.
or doubts?
Yeah, the
Yeah.
questions. Yeah. Okay, I think we did
Okay.
get some sanity checks along the way, so maybe just as a final reassurance, if you feel like the framework was broadly clear, if you could throw in a +1 in the chat, then we could go home happy from
So
here.
can I just summarize in
Yes,
a
please.
minute or so?
It's all yours. Yes.
Okay. I mean, just to I don't know. I don't know if people are just being quiet or otherwise. So let me just
Mhm.
uh, where is the annotation? Okay. So I think the basic idea is that you have this matrix and you get the spanning trees from the diagonals, but the spanning tree also can throw a lot of other things, and the off diagonal elements can throw lots of other things. And the idea is that you want to pair these, whatever comes from the off diagonal and whatever comes from the diagonal, which are not spanning trees. All of those things can be paired in such a way that one of this will have a +1, contributes a +1, then the other guy will contribute a -1. So these two will therefore get cancelled in the super expansion, because the super expansion is a summation over all these possible terms. Okay, so that is the basic idea. The second idea is that because we are doing a Laplacian, remember that we have got rid of the last row and the last column. So if there's a spanning tree, it definitely must have an n in it. If it has an n, then the only way to get an n is for an edge to come in, and that edge has to be a +1 edge, because those are the only edges available for you to reach to n. Okay, and one of the so these will continue. I mean, if this has a child, right, or a parent, whatever, whichever way, so these will all be +1 edges. It will continue. But if it so happens that this is not the case and something goes wrong somewhere, then the way something can go wrong is that you can have either a -1 edge, which is a black edge, and that -1 edge can get into a cycle of some sort. Okay. Or you can have a cycle containing just a +1 edges. Okay. And so this can also happen. You can have a cycle containing the +1 edges. But I think there was a rule which said that if you had a -1 edge, then it can only lead to a -1 edge, which means that if you have a cycle of this sort with all -1s, you could have some +1 edges hanging off it. Okay, you could have some +1 edges hanging off it, but you can't, here you can't have a -1. Well, can you have yeah, if you had a -1 here, then this had to become a -1, and the entire thing will become, a -1 everywhere. Okay, so something of that sort. All right. So -1s will therefore take part essentially in some sort of cycles of some sort. So pick up the smallest cycle by index. So whichever index, whichever node and number is the smallest, pick up a cycle with the smallest index and take that cycle. You're guaranteed that it will all be -1s or they will all be +1s. And then there's a bijection because either you can change all the -1s to +1, the +1s to -1s, and that becomes your pair. And if that is your pair, then you can cancel them off. So the only thing that you'll be left with are things which have no cycles. And things which have no cycles have to be trees. And because they're trees, that n also has to be included in it. Simply because if n was not included anywhere, then you're only looking at n-1 vertices. And if you're trying to fit that many edges, you would form a cycle. Okay, so that is what it is. Hopefully, I mean, if you don't get the entire proof, you can look at the recording, hopefully, and reconstruct the proof. Okay, I'm done.
All right, thanks very much. Yeah, no, that was a wonderful summary. Thank you. I think these are certainly all the main highlights and the main ideas. And yeah, I guess we do need this fact that if you're trying to squish n-1 edges into n-1 of your vertices, then you will end up seeing the cycle. And all of these other elements, I think the bit about knocking off the last row and column, that, I mean, the way that plays into it is also, I think it's really interesting. The -1 anchor kind of comes from there, the -1 anchoring the spanning tree structure. Sorry, the +1, because the -1s are gone from the last row and column, but the spanning tree is obliged to pick up that guy. And the only way it can do that is through these +1 edges. So somehow these diagonals, therefore, neatly contribute to all the spanning tree detected graphs. But there's also a lot of junk, but fortunately the junk cancels out. And this, I think, general theme of junk canceling out nicely comes up, I think, quite a bit. It's sort of a recurring theme. I don't know if we'll see it more in the miniatures, but certainly a lot of inclusion, exclusion-based ideas are also kind of leveraging this idea of all the bad stuff somehow cancels magically and nicely. So it's really nice to see that sort of theme come up here and be so useful and really remarkable in terms of just what the result looks like. Is really it's a really clean statement. And I think a specific corollary mentioned in the miniature is that if you had a complete graph, which means that you can literally see any tree structure is going to show up in the space of spanning trees because all the edges are present. So it's basically is also giving you a count of the number of labeled tree structures that you can have. And if it's a complete graph, you can check that the way the Laplacian is extremely structured, and you get like something like n raised to n-2 or something like that when you apply this formula. So that's a cool consequence as well. And yeah, I think we've probably had I don't know if this is a happy record or not, but this is probably the longest we've spent on any of the miniatures. I know error correcting code split into 2 sessions, but I don't think either of them went past 11, like both of our sessions did here. So I think I grossly underestimated the time that at least I would need to convey the ideas in here. But I think the upshot is that it's a really cool result. So I hope that we do feel that it was worth the time. And tomorrow we'll come back and look at matchings. And that's also a very pretty set of ideas, but I'll try to contain it in one session. I'll do my best to do that. But yeah, in the meantime, I don't know, are there any other quick comments in the chat or any closing remarks or questions?
Yes, the only other comment I had is a quibble
Mm-hmm.
that these are, I mean, well, I don't know, at least in the work that I have seen and whatever papers I've written, these are a bit more than bijections. So we call these as involutions, actually. Bijections typically would be used as a term when you have a different, two different spaces. Here you're trying to map something to itself. Okay?
Yeah.
And so these typically go by the name involution. Yeah. That's
Okay.
a quibble on terminology, but
No, that's perfect. Okay, I learned something new. I will keep that in mind. I don't remember if that there was something that I made up or it was there in the miniature. I'll check, but yeah, that's
probably it is there in the miniature, but in any case, I think
in any case, yeah.
in the research community, the involution is this proof would be an involution proof.
Right. Okay. Yeah. Yeah. I think that sort of makes sense. Absolutely. That's good to keep in mind. And yes. Okay. All right. I think yeah. Thanks for the comments in the chat. Appreciate it very much. And thanks, Vinay, for all the help and also for pulling out the highlights and giving us such a nice summary at the end. I think it's a great note to stop on, perhaps. And once again, thanks everyone for being so patient about staying all the way. See you tomorrow. We'll talk about tilings of a board and what it has to do with counting matchings. So see you then. Thanks. Good night.